Hey, I'm Pamela, and I'm going to be talking about building a MCP server for your Postgres database. We're going to look at the range of ways you can build MCP servers from very exploratory servers where the agents can send full SQL queries to your database and do all sorts of things, maybe things you don't want. And then look at fully typed operational servers where you can have maximum confidence in the SQL that's going to get executed, but agents can still get their questions answered. So join me to learn more about building an MCP for your DB. So my job is to help Python developers build with new technologies. And for the past year, it's been all about MCP. It's the hottest new technology and the first standard to really get embraced by all of the generative AI industry. And people are really excited about it. So I'm excited that I have the chance to talk about MCP for the Postgres audience. So let's start off with a little demo that I recorded where I use GitHub Copilot to ask a question. Here, the question is, hey, which bees are active in El Cerrito in April? That's where I live. So now GitHub Copilot, the agent is thinking, it's using Opus 4.6 to think about this, and it sees that it has an MCP server that it can query to get back an answer. So it's, okay, I can query this database using this MCP server. It queries it, runs some SQL, gets back a bunch of rows about bees and observations and says, hey, the top groups are bumblebees. And I can confirm that that is correct because I can look outside right now and see bumblebees all over the garden. So this was just an example of how we can connect agents with MCP servers in order to get our questions answered and get our jobs done. So what even is MCP? It stands for Model Context Protocol, and it is a open protocol that defines how AI apps and agents can get context from external tools and data sources. Now, this protocol was first proposed by Anthropic, but then it got adopted by everything, and now it's part of the Linux Foundation. So it is a full, proper open protocol. Before MCP, when we wanted to integrate AI apps and agents with different data sources, we'd have to come up with these custom integrations. But now, thanks to MCP, we simply put an MCP server in front of each of these data sources, and that creates a common protocol for getting information from them. Now, one of these data sources could be a Postgres database, and that's what we're going to dig into. So let's actually build that MCP server that I demoed. Now, what we're going to see is that there's a range of ways that we could build an MCP server on top of a Postgres database. On one extreme, we have exploratory servers where the agent can actually write the entire SQL and send that whole query to the database. And that's where you're really putting a lot of trust in the LLM and the agent. But there's a lot of risks there. So on the other extreme, we have these more operational servers with these fully typed constrained tools where we don't have the risk of full SQL. And then we've got options in between as well. So we're going to explore that whole progression today. Let's start with freeform SQL. It has the maximum flexibility, but also the maximum risk. So here is our simplified Python MCP server code. So we create a server using FastMCP, which is my favorite way to build MCP servers in Python, a very, very popular package. And then we define two tools on this server. The first one is a tool that gets the database schema. So we say, okay, when you call this tool, it's going to do this SQL statement that gets back the schema and then dumps it back as a string. Then the next tool can actually take in a SQL query, any SQL query, and then it's just going to execute that SQL query against the database connection. So that SQL query could be a select, but it could also be an insert, update, or delete. Right? There's a lot of options for what you can execute on the database. So what that looks like in action is actually what we saw in the demo already is that, first the agent says, okay, I'm going to call that schema tool in order to find out the schema of this database, see what tables are available, what columns they have. And then once it sees that, then it can execute the SQL against those tables to get back the answers that it needs. So this works, and I was able to get my question answered, which is awesome. But there are some definite problems with this server. So the first is that schema tool. It dumps everything, the whole schema. In this case, that's not a big deal because this is actually a small demo database, which only has 5 tables and 60 columns. But you can imagine in actual databases, you may have hundreds of tables, thousands of columns, and that schema is just too big, right? Like it's going to confuse the LLM. We've seen so much information, most of which it doesn't need, and it may exceed the context window of the LLM because LLMs do have limited context windows. So you're not going to always be able to have a tool like this that dumps the entire schema. What you can do instead is that you can have the kind of progressive schema discovery. So you can have this list tables tool that'll just give back the names of the tables. You can even describe each table. And then you have a describe table tool, which is going to get back the columns for a specific table. So if we give these tools to the agent, it's going to first call list tables to see all the possible tables it could use. Then it's going to call describe table only on the tables it cares about. So in this case, it describes the species tables and the observations table and gets back the columns for each of them. So what you can see is that it had to do 3 calls instead of 1 call in order to get back the schema information that it needed. So that is an increase in calls overall, and that, it may not be worth it to move to this progressive schema discovery tools, but if you do have a really large schema, then it's definitely something you want to consider as a way of, the agent just being able to discover the schema information it needs to answer its current question. Now, a really big problem is mutations without guardrails. It is way too easy to, mistakenly update or delete. So in this example, the user said, "Oh, how many B observations have a low quality grade? Actually, delete those." So the user is actually suggesting they want to delete. Um, but they're doing it in a really, like, casual way, right? So they say that to the agent, and Opus 4.6 is actually like, "Wait a second, are you sure you wanna delete almost 20,000 rows? It's kind of a big deal, right?" And maybe the user would think like, "Oh, wait a second, do I really wanna do that? That's just, like, a lot." Now, Gemini 2.5 just goes ahead and deletes them, doesn't even ask, right? It just goes for it. So, I think Opus is kinda nicer in that it asks for confirmation for, a big deal of deleting that many rows. But here's the thing, is if your tool exposes the ability to do a deletion, there is some agent, some model out there that will do that deletion. So you cannot rely on the safety of models. You have to make your tools themselves be safe, right? And that's what we're going to look at is how can we make the tools be safe? So the one option we have is to try and enforce read-only SQL. Just allow selects. That's it. Only safe selects. So here we have the code for a read-only SQL tool. It has this read-only hint at the top, which annotates the tool as read-only. It starts off with checking the SQL statement to see that it is only a select statement, and then it executes that statement and it limits to a certain cap so that it's not fetching too many rows. So there's a couple interesting things here that we'll dig into soon. Now, when we actually use this agent we use this MCP server from the agent, we can see that it is able to send a complex select query and execute that query and get back the response. So we can still use this tool to answer that question I had earlier. So how do we enforce the read-only? So the first thing is we have that read-only hint. You saw that that was on the MCP tool. Read-only hint equals true. This is something that's in the MCP spec where tools can be decorated to describe how they work. So there's like read-only, idempotent, destructive, etc. So in this case, we're saying, hey, this is a read-only tool, but it is only a hint. It is a hint that MCP clients can use, and they might change maybe the way the tool is rendered, maybe change the way they do approvals. But it's really just to be used for UI because the thing is that it's only a hint. It's not a contract. It's not a guarantee. So you could totally annotate a tool as being read only, but in fact, the tool might allow non read only operations, right? So it is up to us as the developers of the MCP server to make sure that the tool is in fact read only if that's important to us. So how can we do that? So the first thing we have is that call that validates the SQL. So this call uses the library in order to parse the SQL statement into an abstract syntax tree, an AST, and then checks to make sure, hey, there can only be a single statement here, not multiple statements. And that single statement has to be a select statement. Can't be insert, delete, update, etc. Right? So that actually does block a lot of potential, queries that could go through. So it'll block any sort of invalid SQL. It'll block multiple statements like this one. It'll block a delete for sure, and it'll still let through the select statements. That is our first attempt at enforcing read only. The next thing we're going to do, and this is really important, is to enforce read only at the database level. So we can do that at when we set up the connection. We can say, hey, for this connection, it is default transaction read only on. So that's going to say only read only things can happen. And then even better, we can create a dedicated read-only role and use that whenever we're sending the query. So this role only has the ability to do select on this particular schema in this database. And with those combined, that gives us a high-level enforcement on the database level itself. So that'll block inserts, drops, deletes. It also will block this trickier thing, which wasn't blocked from our parser. So this is a CTE, a common table expression, where it starts with blah, 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 select from. That might have passed through the parser, but it will get blocked from this database level enforcement. And we're still letting through the selects that we want. And what happens is when the agent tries to send in a delete operation here, it'll get back the error response that says, hey, that's just not allowed. You can't do that. And then it'll try and suggest like, oh, maybe you can like try and run this locally, right? So this is the kind of experience we want, is for the agent to realize, oh, okay, this can't be done, and to give the user more information. Well, what we can see is we need a lot of layers of protection to try and make this SQL safe, right? Like we've got these four layers of protection, because you can really construct a lot of tricky SQL queries, and some of them will make it past different layers, right? So that with statement actually passes the parser, but luckily gets blocked by our database enforcements. Now these ones are interesting. You can do these selects with Postgres functions that have side effects like terminations, reading files, etc. We don't want to let those through either, right? Now fortunately those get blocked by using a least privilege role, right? So it's really important that you have that as well. And then we can also have operations that just take too much time on our server, which is basically like DDoSing our server. So you can do a PG sleep function or a cross join that's just way too big. So those we kill using a timeout that we put on the tool and said, hey, this tool can only take 30 seconds max. So we need those 4 layers of protection just to feel confident that we can let agents come up with SQL queries themselves. But are we still confident? I'm still not 100% confident, right? I think there's still a possibility that something could get through that that I haven't accounted for, right? So if I really want to feel very secure, then the best option is to not allow the agent to write the SQL, to not allow the execution of arbitrary SQL statements. So that's when we move to our strictest level of tools, which would be fully typed tools. And these are all using templated queries. So this example here is a tool, a read-only tool. It searches the species table. It takes in specific parameters, the query and the limit, and then it uses this templated SQL query that it passes that query and limit into. And it also enforces a max limit here, so that we don't pull too many rows. And then gives back the typed results based off of the rows. So this is very restrictive, very specific, but can still get back a lot of information. So when we call that, you can see that the agent, instead of passing in a SQL query, it's just passing in the parameters, right? So here it's just passing in, oh, the query is carpenter B. When it calls this other tool here, search observation, that one actually takes 6 parameters. And so the agent's going to suggest all 6 parameters, and those get passed into the template SQL query. So we can do fairly complex queries, but we're still asking the agent just to come up with the parameters and not the query itself. Now, That works in order to answer those questions, but then there's other questions that I simply can't answer with these tools. So if I ask, "Oh, how many total observations are in the database?" the agent realizes, like, it simply doesn't have the tools it needs to answer that question. So that's the issue with type tools. They're the safest, but they limit what the agent can do. So if you are gonna have type tools, you really wanna monitor users and see what do users wanna answer, and then add more tools as you need to. And drink some water. Now, let's look at elicitation. Elicitation is another way we can add a layer of safety. So in this tool, here we're adding a tool for deleting observations. Now, this is a destructive operation, so we've also annotated as being destructive. And so we really want to be certain that the user wants to delete this observation. So what we can do is use elicitations where we say, "Hey, are you sure that you want to delete this observation?" and give the user the option. So the MCP client, like GitHub Copilot, will actually send up a prompt that has this elicitation here and ask the user to confirm that they want to do this operation. And then depending on what the user says, so this is actually, getting back input from the user. Depending on the user's input, we're either going to go forward with the with the deletion, or we're going to cancel it. So this is what it looks like in VS Code. So it runs delete observation and says, "Oh, you're about to permanently delete this row." And what's nice here is that I can give more information about what they're going to delete because I've already looked it up in the database. And so then the user can like really think like, "Oh, wait a second, maybe that's not the one I want to delete." So I think this is a really nice user experience. And so then I can confirm yes or no, and then the tool can decide to delete or to cancel the deletion. Now, you can use elicitations for all kinds of things. So I think it's a really great thing to use when you're doing any sort of destructive operation just to double check. But you can also use it if there's any sort of ambiguity, in the user's query, or if you want to refine the parameters, if you want to suggest a different sort of a query or parameter. Uh, there's many things you can use it for, right? Just imagine all the things you might want to throw up an additional prompt for and get back more information from the user before you continue on. Okay, so we've built the tools, we've got this all range of tools. Now, as you're getting excited about building tools, you might want to build more and more tools, right? And you might have, dozens or hundreds of tables that you want to build tool for. Well, then as you build more tools, you're going to have the problem of the agent having to select between those tools. When an agent only has a few tools to pick from, it can do a great job. When it has more and more tools to pick from, and those tools are increasingly similar to each other, it can have a harder time picking which tool is going to be the right one to answer a particular question. So I wanted to talk about this tool selection problem and do a little experiment to think about how we can handle this. So for my experiment, I added two tools. The first one is search observations, and that is searching recent B observations from 2020 to present. And it says that you need to use the other tool for older ones, and you need to call both tools if you need to span all years. And then the second tool is searching the historical observations before 2020, and it has the same tips about the other tool and to call both tools. So you can see these tools, they know about each other, they reference each other in descriptions, and so the agent is going to get all this information. Generally, when an agent is looking at an MCP server, the information it gets is the tool names, the tool parameters, and the tool descriptions. So this is actually all prompt engineering, is deciding what you're going to put in those names, parameters, and descriptions to help the agent decide which tools to use and what to pass into those tools. So then I ran a little experiment, right? If I send a bunch of queries that should need both tools, how does, what tool does the agent decide to call? So here we have some successful queries. So I said, oh, past and present, it called both. Compare 2010 versus 2024, called both. Compare these 2 years, called both. Okay, great, good. But then there's other ones like, oh, have we ever seen these leafcutter bees? All right, it only called recent. Include all years, only called recent. All records in a year, it only called recent, right? Full history, only called historical. Always historical, right? So these are all examples where it should have called both. but for whatever reason, it only called one of the tools. And that means that the answer is not going to be a full answer. It's not going to be a comprehensive answer. It's not going to be an accurate answer, right? And that's a big problem if people are expecting to get accurate answers from these coding agents. So, in this case, we really do not want to have to make the agent choose, right? If you have these two tools that are so similar, so ambiguous, it can be just too confusing for the agent to decide between them. And, it's just not going to call them in all the situations you want them to call them. So in this particular situation, we have a few possible fixes. One fix is that we could return a hint in the result from each of the tools that says, "Oh, okay, this tool only covers this kind of data. For the other kind of data, use the other tool." Right. And so that kind of might remind it like, oh, good point. Maybe I'll call the other tool and so it'll do a follow-up tool call. The other thing that would be nicer that would be more agent friendly is to add an additional tool or a different tool actually replace take out those tools and instead define a search all observation tools, and that tool is just going to query both tables internally, right? So we shouldn't expose the data split to the agent. We should just take care of that behind the scenes. And then, of course, you could just refactor the tables in your database to keep everything in one table, and that might make things easier for lots of people, not just your agents. But generally, this was a specific example where we have a tool selection problem, but you're going to have other kinds of tool selection problems. And they all follow a general pattern where if you have tools that are too similar to each other, where it's really not clear to the agent which of the tools are going to answer the question, then you have the risk of it not calling the right tool. So what you want to do is think very carefully about tool descriptions and names and consider, whether you're defining the right tools, set up some evaluations like I did and see what the agents actually do and decide, do you need to change your tool design, merge some tools, make some changes. Okay, so we've looked at a lot of ways to build MCP servers on top of your Postgres database. As we saw, you can do these more exploratory servers where you're letting the agent send in the full SQL. And that has the advantage that you can answer all sorts of questions that way and can be really useful, especially for people who are using databases internally and need to get a lot of questions answered. But it has this huge risk of, you know, allowing all sorts of SQL operations, right? And then on the other side, we have those fully typed tools, but they can only answer a more limited range of questions. And then in the middle, we have the read only SQL queries there. So you can figure out where you are in the spectrum, what is going to work for your situation. You want to mix and match different things here, but definitely keep in mind all your options for how you can, enforce that only the operations happen that you want to enforce, because you can enforce a lot of this at the database level, and that is going to be your safest approach. And then adding more layers on top. Because it's really powerful to build MCP servers for your databases. So I want to encourage everyone to do it, because it can really empower your users, whether they're internal users or external users, to be able to use natural language to interact with the database. So definitely do it, but keep all of this in mind when you are designing your servers and consider how you want to go about your server. So thank you so much for watching. You can grab my slides from this URL here. You can grab all the code from this repo. And if you have any follow-up questions, you can always hit me up online and I'm happy to chat more about MCP. Bye, everyone. Thank you.